Okay, I'm going to be doing problem 7 here, which has two shafts which have a center distance of 20 feet apart, and they are connected by a flat belt in which there is a 15-inch diameter of the small pulley driving the second shaft at half its angular speed. So this driving pulley is powered by a nominal power of 100 horsepower, and that speed N1 is going to be at 1140 revolutions per minute. So the application requires a service factor, KS of 125, and it looks like that the belt we're using is a polyamide A5 belt. And we're going to assume that the belt's tight side tension is at its maximum value. So the question or the goal here is to determine the smallest belt width in which this system will not slip. So a belt usually slips when the force that is transmitting exceeds the maximum frictional force between the belt and the pulley itself. So to check for slipping, we're going to use this belting equation as given here. So previously on this example, I went through and in a lack of time, I wrote down as many equations as possible. I wrote down the length equation, which was not needed. I missed some simple things such as a conversion from feet to inches down here that just needed to be converted to inches. I misunderstood what this N value was from the design power, which was supposed to be factor of safety, but I assumed it to be the rotational speed. And I also had some slight mix-ups with understanding how the weight was related to the specific weight. And then understanding from the example problem that uh, the maximum value of the belt side tension is what it was at. So that is why the FA turns into that T max. So how to check for slipping? So of course, using that belting equation is a good start. However, I think writing down every single thing that is known is the approach. So I wrote down the center distance, the diameter, the nominal, the everything said in the problem statement, and then we got down to we were given that this rotational speed of the second pulley is half of the first. So given that, we just half the rotational speed and we get 570 for the second pulley. Now the larger diameter is able to be retrieved from the relationship between rotational speed and diameters. So with this relationship, we're able to see that 1140 over 570 is going to give us 2, and the small or the large diameter is going to be twice the small diameter of 30 inches. Now we're able to try to break down what everything in this slipping belting equation means. So this phi sub d is going to be given to us by pi minus 2 arc sine, difference in the diameters divided by 2 times the center distance in radians. Now, this angle here is going to be the angle from where it is tangent with the belt going off of the pulley itself, and it wraps all the way around is how we actually get that. So the next value we have here is this F, which is the coefficient of friction, which is tabulated. The force 1 is this force on the tension side, which happens to be on the bottom in this case. And it is going to be equal to this FA times the width and these correction factors, where FA is going to be tabulated, which we're going to call is at that max T, and B is considered to be the width, CP is tabulated, and CV is going to be equal to 1, where it is 1 for everything except for leather in this case. So for this F2, this is going to be kind of the slack side, and this is the top where it's going to be that tight side minus 2 times the required torque divided by the small diameter, where we can get this required torque by this relationship with 63,025 times the design power, which is then divided by the rotational speed, where this design power is given us by the nominal power times this factor Ks and our factor of safety Nd. So the centrifugal force, which is going to be the force that is going to be the centrifugal hoop tension, is the weight divided by the gravity times velocity squared, where weight in this case is going to be equal to the specific weight times the thickness of that belt times the width of the belt, and v is in the speed, of course. So now we can go on to the solution where we just start by pulling values from the table. So we assume table 17.2, we have the A5 polyamide belt, which gives us a thickness of 0.25 inches. It gives us a max tension of 275 pound force per inch. It gives us a specific weight of 0.039 pound-force per inch cubed and a coefficient of friction F of 0.8. Now from the 17.4 table, the correction factor CP with a 15-inch small pulley diameter gives us a 0.72 correction factor. So with that given information here, we're able to start working backwards and plugging into our known values and solving. So the centrifugal force, we're able to plug in that relationship for that weight and really plug and chug. But first, for this velocity, we're going to need to go from revolutions per minute to a more satisfactory kind of unit of inches per second. Now, this is able to be determined by looking at the units of things like gravity and the units that everything is in with the table here is inches and pound force, so it's good to convert feet to inches right away, revolutions per minute into per second, and etc. So doing that, we multiply the original speed by 15 pi per revolution, and we divide it by 60 seconds per 1 minute to get this 895.35 inches per second as the speed. And then the gravity, of course, is going to be multiplied by 12 inches per 1 foot to give us 386.4 inches per second squared. So plugging in all those values, we're going to get the centrifugal force, keeping the B as a constant of 20.228 times that constant B. So we're going to continue solving, keeping these answers in terms of that constant B, which we're solving for. We are able to plug in everything here. The same thing applies here, that CV is 1, that B is constant, CP is the table. So we plug those in, and we get a tension force of 198 times that constant B. Now going on, plugging in more, we're going to, of course, try to keep the units correct the whole time as going through this. We plug in this required torque, and we're going to get that it's going to be 6,910 pounds after plugging everything in. Now, to find this slack side force, it's going to be that force on the tension minus 2 times the required torque divided by the small diameter. And plugging on all those values, we're going to get that it's going to be 198 times that constant B minus 921.333. So now we want to check for slipping. So we have almost everything. The last thing we need is that Phi of D, which we can plug in all the values that we had, making sure we convert that into inches, which I did not do right there. Didn't do it, but that's what you're going to do right there. And once you're able to plug everything in, you're going to get that in radians of 3.0791 radians. Now we're going to go ahead and use that Belting equation, plug in everything. Now the goal is just solve for B, solve for that width. So solving for that width, we can just find that it's going to be 5.689 inches from reducing all of this. So this is saying that in order not to slip, this belt must be at least 5.689 inches. So that means that that force will not exceed the maximal frictional force as long as the width of the belt is given that.